Hi everyone, I'm Federico Masiero, MATLAB Student Ambassador of the University of Pisa, and today I'm going to present you a seminar on supervised learning. I remember to you that if you're missing the event for any reason, or if you're missing a part of the event, you can watch it at any time in the future, because this will be uploaded in our YouTube channel, and also the material that is presented during this seminar will be available for you to play, either the slides and the MATLAB scripts that I will show you. So this is the presentation. You see the title is, as last time, just machine learning with MATLAB, but of course the contents are all updated. Today the outline of the presentation regards an introduction to supervised learning first. Then we will move to classification, and in particular, talking about classification, we will see K-nearest neighbor, decision trees, support vector machines, and these are mainly the three algorithms that we will see to train a classifier. Then we will talk a little bit about how to evaluate a classification model and how to improve our predictive models. And in the last part of the presentation, we are going to talk about regression, and in particular about linear regression and regularization techniques such as ridge, lasso, and elastic net. So okay, this is the big picture. As last time, as you may remember, I told you that machine learning is a subfield of AI which tries to learn from experience, learn directly from data, and this is really useful, especially if we don't have the possibility to build on our own a model of the data because the mathematics is too complex or for any other reason. And there are mainly three approaches, as I said last time, which are supervised, unsupervised, and reinforcement learning. In these couple of seminars, I discussed about unsupervised learning and supervised learning, and in particular, today I'm just going to focus on supervised learning, and in particular on these two subgroups of analysis of supervised learning, which are classification and regression. So let's start with an introduction on supervised learning. Supervised learning deals with the problem of learning a function that maps an input to an output based on exampled input-output pairs. That means this time, if we think that our machine learning algorithm is the robot of this picture, a supervised learning operates using a kind of supervision. That means we have the possibility to tell the algorithm which is the ground truth of the data that we want to model, that we want to predict. This is a funny picture because you see that the robot that in this metaphor is the machine learning algorithms is trying to ask into the pictures of apples if they are bananas, and of course the supervision part of the algorithm says no, and then instead when the robot is able to recognize that they are effectively apples, the man starts to say yes. So as I said at the beginning, there are two main approaches adopted in supervised learning, which are classification and regression. Classification aims to assign to each input one among the finite number of discrete categories that we have in our dataset. Instead, regression aims to assign a desired output which consists on one or more continuous variables. So the main distinction between the two is that, of course, since they are supervised learning algorithms, approaches, we have the ground truth of our data. But in one case, this ground truth is represented by a discrete finite amount of categories. In the other case, in the case of regression, we have that the class, if it could be called class, the response variable that we want to predict is a continuous variable. So supervised learning is a two-step process. Instead, if you remember last time when we talked about unsupervised learning, we were just diving into the data without getting care to split, okay, our procedure in steps. So first of all, the first step is model construction. In model construction, which is also called a learning step or a training phase, the model is built by exploiting a set of tuples, also called samples or examples, and each tuple or sample is assumed to belong to a predefined class, the same class that I told you before, that could be a finite amount of categories in the case of classification, and a response continuous variable in the case of regression. And the second step is the model usage, also called testing phase. To classify, to predict future and unknown objects in particular, we reserve an independent part of our original dataset to estimate also the performance of our algorithm. And if this performance is acceptable, we will use also our predictive models to work with new unlabeled data, so data in which the ground truth is not available. This is a graphic representation of what I already said. In model construction, we just take a part of our data set called a training set. We use this part to train our machine learning algorithm, and this, after a bit of tuning, will give us a model. This model will be then used with the remaining part of our dataset, which is called test set, and with the test set we are going to test our model and see what is the inference capability of our model, its generalization capabilities, and if it is good enough, we can use our model also with unseen data for which the ground truth is not available. So for those of you who are new to the field, you may ask yourself, why do we need to split the dataset? Why do we need, in supervised learning, to split our methodology, our workflow in two steps? Why we cannot do just as unsupervised learning, that we gave all the dataset and the learning algorithm just playing on its own, discovering patterns in data, using the labels this time? So the reason is related to the fact that when you also have the ground truth of your dataset and you use supervised learning approach, you tend to what is called overfit your data. So you are also, if you don't split your dataset, you tend to model also the information part of your dataset, which is noise, which is irrelevant, which is redundant. And so typically what happens is that if you use just all the data that you have and you build your model, the result is poor, just because you are building a very complex model which is able to fit all the characteristics of your dataset, But then if you gave to your dataset, if you gave to your algorithm new data, this will show poor results. So these three images here are put just to highlight the fact that if the new data are the blue ones and you just train your model entirely on the green ones without dividing without splitting your dataset in two, the risks is that you achieve a squiggle line, as you can see on the right, instead of properly modeling the data, as you can see in the center of the dataset. Sometimes it may also happen that if you catch a bad partition of your dataset, the risk is that you model very badly your data. And this is the case when you typically underfit and not overfit, meaning that the complexity of the model that you're trying to fit is smaller compared to the complexity required to effectively explain the variability of your dataset. So to answer to this question, we need to split our dataset because we want to generalize. We want to build a model able to understand also what's going on with new data, and which is learning not just the structure of our dataset, but is learning something meaningful. So typically in machine learning classes, what is typically taught to students is that the error of the model can be decomposed in two sources. The first source is the bias error, and the bias essentially is the error from wrong assumptions, and it typically leads to underfitting, what we called underfitting in the previous slide, meaning that we are missing something in our data. We are missing information. We just put some of them inside, but we're building something that is too simple to explain, to build a predictor. The other source of error is the variance, and the variance instead is an error from the sensitivity of small fluctuations. In particular, if you tend to use all your data set to train your model, what typically happens is that, as I said before, your classifier tends to model also the small fluctuations that are present in the data set. Also, noise could be present, since most of the times the collected data comes from measurements, and if the variability is not properly accounted for, so if you're just learning also the wrong variability of your dataset, you tend to overfit your data and learn something that is not correct. So this is a nice picture to explain what typically happens. So from the theory, we know that the mean square error, which is a nice metric for statistical estimators and also classifiers, can be decomposed in the variance plus the bias squared. So from this picture, you can understand that as the model complexity becomes higher, typically the training error becomes smaller, but you are reducing the bias, but you are increasing the variance. So as the model complexity increases, also the capability of your model to handle the noisy part of your dataset and the high variabilities that are present becomes smaller. Its capability becomes smaller. In fact, the typical aim of a machine learning algorithm is not just to minimize them together, in the sense that we don't want just minimize the MSE, but we want to minimize its components correctly to achieve the best MSE that we can find from this specific problem. As you can see also from this picture, typically when the bias is large and the model complexity is small, you are in the so-called underfitting zone, the zone in which typically there are some wrong assumptions in your model, and as it is said in this graph, the complexity that you adopted to describe your dataset is not enough. Instead, if you see in the right part of the graph, that is the overfitting zone, meaning that in that specific cases you are able to reduce effectively the bias, but there is too much variance, meaning that you are learning also noise and high variabilities in the data. So when I see these pictures, typically I'm like this. So this is the main aim of your machine learning workflow. You want to minimize MSE, but you have to take care also to the graph on the left side, because it's not easy to handle with variance and bias. Typically, this is called in machine learning lingo the bias-variance trade-off. So, as last time, I want to show you our convention that we will use during the presentation on how we decide to organize our dataset, our variables. Specifically, if this is the matrix of our data, if X is the matrix of our data, we decide we will collect all the features along the columns and all the observations along the rows. And in particular, this time, differently from the unsupervised learning approach, we will have one column more, which is the Y column, and this represents the response variable or label. And I remember you that if this vector is vector of continuous numbers, continuous variables, this will be a regression problem. Instead, if this Y vector is a vector of nominal variables, such as strings identifying the class, this will be a classification problem. So let's start with classification. If you remember our big picture, now we are here. And in MATLAB, you can do classification using the function fitC, completing with the name of your classifier. So the syntax typically is fitC KNN if you want to fit a KNearest neighbor classifier, fitC SVM, fitC tree if you want to train a decision tree, and there are many others. So there are two main syntax with which you can do this. The first syntax requires you to play with just arrays, so you have to organize that data. As I told you in the previous slides, you have a big matrix X of observations explained by their predictors or attributes or features, as you want to call them, and you have another array which is the one collecting all the labels of your data. Another possibility is to use tables, the data structure offered by MATLAB, in which you can collect any kinds of data type and organize them as it is just a big cell array, but with some other properties that are useful to play with. Because with tables you can also merge tables. You can also split them. You can do very fancy stuff, because all the columns that you have are labeled. As you can see here, all of them have a name variable, and it's a very useful data structure that you can use. If you are not familiar with, I recommend you to watch some other videos in our channel about MATLAB fundamentals or MATLAB on-ramp, in which they can explain to you what exactly are tables and how to play with. You can also train your classifier, use your classifier with an application available in MATLAB, which is the Classification Learner. You can access the Classification Learner going to the Apps menu, and then if you have the machine learning and deep learning toolbox, you can find easily the Classification Learner as one of the many applications available to you. As you can see, there are many others, such as neural network toolbox for clustering, for fitting, for pattern recognition. Actually, we haven't talked yet about neural networks, but maybe in a future video we will talk. We will reserve a dedicated seminar to how many things we can do with neural networks. So let's start talking about the classification algorithms that I want to show you by talking about KNearest neighbor, which is probably the simplest approach that we have for solving classification problems. And I would like to start this introduction by reading to you this sentence, which comes from the video linked here in the slide, from an MIT professor, which was starting introducing machine learning, and in particular supervised learning. So as this professor said, if something is similar in some respects, is likely to be similar in other respects. Fairy tales, legal cases, medical cases, business cases. If you can see that they are similar in some respects to a similar to a situation, you've got now, then that's likely that they're going to be similar in some respects as well. So when we are learning, we are not just learning to recognize a category, we are learning because we are attempting to apply some kind of precedent. Why I decided to read this to you? Because there are some classification algorithms which are not really able to learn something from dataset, but they are able to recognize something because they look for a precedent, for what they already have in memory. In particular, we are now going to dive in the KNearest neighbor classifier. The KNearest neighbor classifier, if the color data are the data that we have in our dataset, and we want to classify an unknown datum, the algorithm is based on the search for the k-nearest labeled point to the unknown data. In particular, if we have a 3 nearest neighbor classifier, this will look at the 3 closest labeled sample to the known data, and it will classify this datum by a kind of majority voting. So if the highest amount of data closest to the unknown datum belongs to the green class, this point will be assigned to the green class. So as you can imagine, with if you remember what I said at the beginning, that we have a two-stage process, here there's no real learning. here we have our label examples, okay? We build our, we just collect them in a, we just collect a part of our training set without building something, and we just, with these labels that we have, we just compute distances and assign to the unknown points their class based on these distances. This kind of approach is called lazy learning, or instance-based learning, based on instances, because here you just have things, data stored in memory, and you just look at the closest distance to an unknown datum to the ones already labeled that you have. So what about this case in which if you have an unknown datum which is whose distance is equal for three different points belonging to three different classes. So in that case, typically what happens is that the algorithm just randomly selects the class among the ones with more closest examples. So in binary classification, it's easy to deal with this problem because you just need to set the number of neighborhoods, the number of neighbors to be odd. And if they are odd, you will for sure have a majority voting. You will for sure have a winner. In case of more than two classes, it's difficult to obtain this behavior, but you can try to select different values of k in order to avoid this condition. You can fit a KNN classifier using this syntax. In particular, fit cknn is the function that you have to run. You can pass to this function your matrix of predictors and your array of response variables. But you can also pass to your classifier a table and telling to the function which is the name of your response variable, as I suggested to you at the beginning of the video. There are many options available when you're doing the training of your KNN classifier. One is the distance metric. As I tell you, this classification algorithm is completely based on a measure of distance, and in particular by tuning this distance metric you can obtain different behavior, and this is a really useful parameter, especially when you're dealing with high dimensional data, because there are some matrix, as I explained to you in the previous video, which are less sensitive to the number of dimensions with respect to others. And one example is the cosine similarity or cosine distance. Then another option is the number of neighbors, which is by default 2, but as I told you is an important parameter because in some cases it is able to deal with the problem that we don't have a winner. We have for instance the same number of points distant from your unknown data, which are red and green, so the same number of data. So as an example, if we are in the case of before and we have a 3 nearest neighbor and the 3 closest point belongs to the 3 different classes, in that case it is better to select a different number of neighbors. Of course, this is something that you are not able to understand it just by selecting but just by looking at your data set. You should play with your training and build different models with different K to understand which is better. And also another option is to add weights. So another possibility is to not just decide the winner based on the closest example, but you compute a kind of average, which is weighted depending on the distance of your unknown datum to the closest labeled ones. So another kind of classification algorithm instead is the decision tree. Decision tree is a flowchart-like tree structure, and in particular, as you may know, trees in computer science are a data structure in which there are some nodes, and these nodes can be internal or external. If they are internal, that means that they have no children, meaning that from that nodes there are no branches starting from that node going away, but they just have branches pointing to that specific nodes. And these internal nodes, that can also be defined simply as known leaves nodes, are the root and all the other with no children, which are indicated with just the circle in this figure. Then there are the branches. The branches represent, for our classifier, the outcome of a test. Sorry, I forget to tell you that each internal node in a decision tree is a test on an attribute. So if your attributes are, for instance, height, weight, and others, each internal node represents a test on one of these features and could be an example of: is the weight larger than a certain threshold? If the outcome is larger, you may go in one branch. If the outcome is smaller, you may go in the other branch. Okay, so internal nodes represent test on an attribute. Branches represent the outcome of these tests. So as you can see from the picture, if this node represents a test on the attribute x1, which is one of the predictors, if x1 is larger than or equal to this threshold, then you should go in that way, meaning that the outcome of this result for a sample of your dataset you should look for its label in this direction. Instead, if the outcome of your result is smaller than a given threshold, you should go in the other direction. Why you move based on testing, based on tests on attributes? Because when you reach a leaf, a terminal node, an external node, this node holds a class label. So if you start with an example which has x1 greater than 2.45 and x2 greater than 1.75, this classifier classifies this point going in this direction and then in this direction based on these two outcomes, based on these two tests. And what is really nice about this kind of decision algorithms is that they are very nice to extract if-then rules, which are rules really easy to handle and which can help you to understand really how your model works. So this is maybe something a little bit more complex in regards how the training process works. So how we build this structure, because this is an already trained tree. So the inference process works just by testing a sample against the decision tree. When you test a sample against the decision tree starts by testing its attributes, and based on the outcome of these tests, the decision tree classifies the particular data points. The tree is built with an algorithm that in computer science lingo is called greedy, meaning that we build our tree in a top-down manner. We start from the root, and then recursively we go down from the different branches, and we decide to partition the different nodes of the tree based on some attribute selection measures. So we start that all our samples or all our training examples are in the root of your tree, which is the unique node at the beginning, and then we start split this in order to partition our data, in order to find what are also called pure partitions. So partition in which we try to find only points belonging to unique classes. And how do we decide the way in which we have to make this partition? We decide based on some statistical measure which helps us to decide which attribute we should select to do the test, essentially. And then also the number of splits is also a parameter that can be specified in order to decide at any step an internal node how many times can be splitted. So how many threshold you can apply to a given attribute. Decision trees typically suffers from problems related to repetitions and replications, which means that typically a tree, when it's built, have some anomalies. Sometimes you may encounter the problem that an attribute is tested twice in a similar manner, as in the example on the left, and this is a repetition. But you also may encounter problems such as replication, in which an entire part of the tree is completely present in two different sides of your decision tree. These problems came out due to noise and outliers, and this problem can be handled by pruning the tree, so by removing these pathological branches, and in particular this kind of effect is also useful to avoid overfitting. How we train these models in MATLAB. In MATLAB we have the fitC tree function. The fitC tree function, as the other fitC function, fit classifier function, needs the data matrix X and sorry, here there are some errors somewhere, and your vector of labels Y, and it returns you a decision tree model. And in particular, there are some options here that you can specify, and these options are especially useful for the things I explained you before on the training process. Some options are the splitting criterion, the mean leaf size, and the maximum number of splits. So the maximum number of splits decides how many times you can, how many branches can be obtained at maximum based on a test on an attribute. The mean leaf size gives you a minimum number of observations that you should keep during the training process on each leaf. And the splitting criterion is a kind of formula that is also the attribute selection measure that gives you selects you the best way to find splits in the dataset, and these are typically statistical measures that aims to find the best attributes to find the best splits. Another classifier that I want to talk with you today is the support vector machine. Support vector machine, which is originally used for binary classification, aims to respond to the question: is there a best way to partition these two classes? Is there a way to find a kind of decision boundary which is the most suitable to divide these two classes? So the answer is yes. There is a classifier able to do this, which is called, as I said, support vector machine, and this classifier is used to find the largest margin separating hyperplane, how it's called. So as you may know from linear algebra courses, hyperplane is just a big name to call a line in 2 dimension, a plane in 3 dimension, and every element in n dimension which is able to separate data. And in particular, if we are in n dimension, such element, such hyperplane has n-1 dimensions. So support vector machines, so this largest margin hyperplane is built on a convex optimization problem, to be honest, a constraint convex optimization problem, which is based on this statement. Essentially, you want to minimize the norm of your weight vector, how it is called, and your weight vector is a vector of parameters that essentially helps you to build your decision boundary, your hyperplane. And in particular, you want to minimize the norm of this vector such that the constraint that you see below is satisfied. That means epsilon y, which is equal just to -1 or 1, depending on if you are choosing one class or the other class, since it is just for a binary classification problem, times the dot product, the internal product of your weight vector and your data sample plus the bias is greater or equal than 1. I don't want to stress you. I also put here this kind of GIF meme. This is just for you if you're curious to understand how this exactly works. When you use MATLAB, you don't have to take care on this. If you're curious, I put here the link to a Stanford lecture on SVM. But I just wanted to show you, coming back to the previous slides, that this constraint is the constraint that leads you to find these two margins. So fixing these two margins is exactly the constraints that you need to fix to achieve a solvable optimization problem. And then the aim of your classifier is to minimize the norm of your weight vector W, which is a vector of parameters, as I told you, and is the one that is used to find your decision boundary and also your support vectors, as they are called, these two lines that there are the two margins. And by minimizing the weight, the norm of your weight vector, you are actually increasing the margins of your classifier. So you are actually trying to find the equation of your decision boundary in which for which your weight vector is brings you to the largest margins. By the way, thank you for the questions, Apo. Thank you very much. What about non-linearly separable problems? So, as I told you, these algorithms find an hyperplane, but sometimes you are not able to classify data based on just hyperplanes. This is the simplest approach that we have, but is not really helpful in some cases. As you can see in this case, in this picture of the input space, for that specific scenarios, the support vector machine adopts what are called kernels, which are functions which moves our input space into another feature space, how it is called. So essentially it is a mapping, here represented by a phi function, which brings our input space into another space called feature space, in which most likely the problem is linearly separable. So in these cases, when you can't solve your machine learning problem with just an hyperplane, you can use kernels when training your model, and by specifying these kernels, these functions that maps your data set in another space, then the training algorithm keeps learning the largest margin hyperplane in the new space. Again, even here is not said, but we will see later in the demo. You may also ask me, what about classifying 3 classes with an SVM? So in that case, in particular, there are many approaches. I think by default, MATLAB gives you learns different classifiers, different support vector machines that aims to classify one class versus all the others. So you should learn in that specific case more than one classifier, and then the inference phase, in which you have to decide to which class the data points belong, collect the information of all the classifiers that you have trained. So by the way, support vector machine can be trained in MATLAB using the function fitcsvm. Again, as usual, you have to specify or x and y as respectively your predictors in numeric matrix and your response variable y, or you can use tables. So you can just specify your table and specifying together with the table which of the variables inside your table is the one containing your response variable. Also here, as you can see, there are many options. Actually, I want to explain you a bit more about this classifier just to understand at least what these options do. In particular, some of these options are the kernel function. So you can specify different ways to map your data from the input space to the feature space to achieve a linearly separable problem. Typically these functions are radial basis functions, Gaussian kernels, Gaussian functions. They are functions that are like this, so that they try to make jumps around the data points that you have in your space, and they decrease with distance. Another option that you can use is the kernel scale, which is just a scaling applied to your data before kernel transformation. By default is 1. So it's a kind of feature scaling before going into the into applying your kernel. And then another option is the box constraint, which is a regularization parameter. Maybe, I don't know if you are familiar with regularization, but I mean, we will talk about regularization later. So I show you also an extra content if you want to try to play with. There are also some classifiers which are called ensemble classifiers, ensemble methods, in which you partition your dataset and you build different models for each partition of your dataset. And in the inference process, you just combine the result of the different classifiers to predict the class of a new data tuple. These approaches are called ensemble methods, as I said. They can be trained in MATLAB with the function fitCensemble, and there are really many ways to do it. In particular, you can select the different classifiers that you want to train for each partition. You can also select the different the method that you decide to use to combine the different outcomes of the classifier. This is a kind of voting method, and also for this there are many. There is bagging, there is boosting, there are many. And I just wanted to show you because typically this is the result when you use an ensemble method. When you want to solve a problem like this with a decision tree, for instance, you will have a decision boundary that instead of being the straight line that you see in the middle of the picture A, is that piecewise linear function, which of course I mean it can become better than this, but one way to achieve a better accuracy could be to combine many decision trees to achieve a more finer decision boundary for your classification problem, as you can see in the right picture. How to evaluate classification quality? So, as it is said here, numbers have an important story to tell, but they rely on you to give them a voice. So when we train a classifier, we also need to find a metric, a way to assess how good it is, and there are many actually. And also the choice on one with respect to another one depends on if you are working with a balanced dataset or an unbalanced dataset, which means if you are playing with a dataset in which examples from the different classes appears almost the same amount of times. So I don't know, if you have 100 a dataset with 100 examples, exactly 1/3 are from one class, exactly 1/3 are from another class, and exactly 1/3 are from another class. But of course, in cases in which you don't have this problem, all of them are valid. So if you have a balanced dataset, how it is called in machine learning lingo, all these metrics are can be used. The most common are accuracy, error rate is its inverse, so it is exactly 1 minus the accuracy. Another very common one is the sensitivity and the specificity, and also the F measures, which can be different depending on the value of beta that you use. you can see here how they are computed. They are computed based on the definition of four kinds of group of examples, which are the true positives. True positives refer to what are called the positive tuples that were correctly labeled by the classifier. Here, positive and negative just is used to understand class 1 or class 2 in binary decision problem, and in particular, often positive examples are used to denote the examples of the class that you want to classify completely correct, which the most important one, let's say. So true positives, of course, are the examples from this class that are correctly labeled, and by contrast, false negatives, true negatives are the negative tuples, negative examples, the examples coming from the negative class that are correctly classified, correctly labeled. And then there are also false positive and false negative, which are the negative tuples incorrectly classified as positive, and the positive tuples incorrectly classified as negatives. So overall, when you have a binary classification problem, you can collect your result in a matrix, which is called a confusion matrix, and it is so small when you have just a binary classification problem, because you have just a positive class and a negative class, and by feeding the amount of entries that are belonging to the predicted class versus which class they actually belongs to, you can find exactly the amount of true positive, the amount of false negatives, the amount of false positive, and the amount of true negatives. In case you have to model a classification problem with more than two classes, typically your confusion matrix will have will look like this, in which we have exactly an n by n matrix, where n is the number of classes. In these specific cases, all the matrix that we defined before, such as the false negative, the precision, the specificity, the accuracy, can be obtained by computing this metric singularly for each class versus the remaining classes, and then by averaging. You can build your confusion matrix, your confusion chart, with these two lines of MATLAB. The first one is used to predict your labels of your test set. So model is the outcome of one of the functions that we discussed before. It is a trained model with, for example, fit C KNN, fit C3, fit C SVM. And the dataset here, the data test, is part of your dataset that you want to classify based on your model. And the metric that are predicted by MATLAB are exactly this, and can be and are stored in predictions, in the variable predictions, which can be used together with the real labels of the data that you used for prediction to build the confusion chart. How can we improve models? Well, there are many methods. First of all, one way is to use validation to tune parameters, and in particular we split we don't just split our dataset at the beginning in training and test, but we also split our dataset in our training set in train and validation, and the part of train is used to change every time the features of our model, the characteristic, the hyperparameters of our model, and the validation is used as a test during the tuning. But this can be done even more, let's say, not more formally, but more in a more rigorous manner with the k-fold cross-validation, in which instead of just partitioning randomly once our dataset, we divide our training set in k-folds, and then these k-folds are used in different iterations to build our model using k-1 folds as the training set and the remaining fold as the validation set. Again, as I told you, these are methods to tune your hyperparameters, and to increase their accuracy. So in MATLAB, you can fit cross-validated models using the cross-val property of the machine learning models and turn it to on, essentially. But you can also use holdout validation, as I told you, by expressing a scalar from 0 to 1 to express the percentage of data that you want for the split. You can also specify, in case of cross-validation, the number of fold that you want. By default, if I'm not wrong, is 10 or 7, but 10 is the most common, by the way. And there is also the possibility to use leave one out validation, which is an extreme case of cross-validation in which the number of folds is exactly equal to the number of examples. In that specific case, if you have n points in your dataset, n examples, n-1 are used at each iteration as the training and 1 as your validation, as your test. You can also manually specify a partition using the CV partition function, and in that case you specify a partition once and then you call your model to be cross validated by the partition that you specified with the CV partition. This is useful if you want to check the behavior of different algorithms, but with the same partitions, for instance. So another way to improve your predictive model is by using feature selection. Feature selection is used to essentially, as the word said, to remove some predictors from your original reservoir of predictors. You just find a way to just select the most relevant ones, and you keep these to achieve a faster and more cost-effective classifier. In particular, there are three main classes of feature selection algorithms. There are the filter methods. Filter methods are those who apply statistical measure to your features, to the different features of your describing your data, and by assigning a score, they select the ones which obtain the highest score based on the statistical measure adopted. There are the wrapper methods. Wrapper methods are those that set your feature selection problem as a search problem, and in particular they try to test different combination of your attributes and different combinations, yeah, in order to find the best combination for your model. And another way is to use embedded methods. Embedded methods are essentially those that learns directly from your data which features are the best to use, that best contributes to the accuracy, for instance, of your model. An example of embedded methods is the use of regularization. So we use essentially penalty terms in the optimization procedure that is behind the training of your classifier. So one thing that I would like to remark is that it is important to consider feature selection as a part of the model selection process. If you don't do this, you may introduce bias into your model, and by introducing it, you can inadvertently go towards overfitting. And also a mistake that is typically encountered when you see machine learning workflows is that feature selection is performed on the whole dataset once at the beginning, and then you decide which model to train and so on. Instead, what you typically have to do is to divide your dataset at the beginning, and then your training set, or the part of your training set from which you decide to tune your model, should go under feature selection. So before starting with regression, I would like to show you a very brief MATLAB script that I want to bring to you. So I move to MATLAB. If it works, it works. So it seems that I'm not able to move to the MATLAB demo. I don't know why. Okay, now I see. Okay, here I am. And this is a very simple MATLAB script in which we can keep together all the things we discussed during the first part of the presentation. So I load probably the most used dataset on machine learning, which is the KNearest dataset, a dataset on flowers essentially, in which you want to predict among 3 different classes of flowers based on some predictors, some features which regard, for instance, the sepal length, the sepal width, and others. So the dataset as is, at least loaded from the MATLAB internal root, has 150 examples, okay? And in this script you can see, we are going to see briefly how we can deal with this classification problem. You can see that After loading the dataset, if you ask to MATLAB to tell you which are the name of the classes, these are the kinds of classes that we have, the kinds of flowers that we want to classify, and if we want to understand how many examples for each class we have, use a cum array, calling the vector containing all the classes. We will easily achieve that all the three classes are equally distributed. All the examples are equally distributed among classes, so we have a balanced dataset. So here I just wanted to show you that here I stored a part of the measures, a part of the features. I stored my example, but just looking at the first two features, because since this dataset is four-dimensional, so since we have four predictors, and you can see them here with this tabular visualization, we have no chance actually to see data in the wall of their dimensionality. So one way to see them is just to see projection of the dataset along a couple, or also three if you want to see them it's three-dimensionally, projection onto two or three features of your dataset. And here is an example, but also what you can do is to visualize all the possible projection. Here is easy to do, just because we have just four predictors, so the number of combination is not that big. And here's the result. If you do this, these are all the projections that we have. This is a scatter plot matrix that can be printed using gplot matrix. Instead, to print just a scatter plot, you can use the gscatter. I prefer to use the gscatter instead of just scatter, because you can also specify to color each dot based on their labels, on the labels of the dataset. Then here we train the four different classifiers, not only the ones that we saw during the presentation, but also others that are offered by MATLAB. For instance, here we built our custom partition. So we use the function cv partition, give the number of folds as k equal to 10, and we built a unique partition that we are going to use for different classifiers. One classifier that we could try to fit is the Bayesian classifier. A Bayesian classifier, they are also called Bayesian belief networks, can be fit using the fitcnb function, and by using and we can use cross-validation for this classifier by specifying the partition that we built here at the beginning. We can evaluate the performance of our classifier by computing the loss of the classifier, which is another way, another metric to understand how well it's performing. And we can also ask to our classifier to predict the results of the classification by calling the function k-fold predict. Here we should use k-fold loss and k-fold predict, because using cross-validation builds what is called a MATLAB an object that is a cross-validated classifier, and cross-validated classifiers needs particular function either for prediction and for computing the performances, which are, for instance, k-fold predict for prediction and k-fold loss for computing the loss and to evaluate the performance of the classifier. Again, the same is done for other classifier, for instance, for linear discriminant analysis classifier, also for a decision tree, and also for a k-nearest neighbor, in which we also specified, for instance, the number of neighborhoods, of neighbors as 5, and we can look at their performance with this bar chart in which we plotted the losses for each model. Another way to visualize the performance of our classifier is by using confusion matrices, as I told you. And since we predicted for each of them the results with k-fold predict, we can use the result of k-fold predict to build the confusion matrices for each classifier. For instance, we can build the confusion matrix of the naive Bayes classifier, for the discriminant analysis classifier, for the classification tree, for the decision tree, and for the nearest neighbor classifier. So that's almost everything. That is also the possibility to do feature selection. Typically, machine learning is an iterative procedure. You start by just training your simplest model, and then maybe you're trying to change things to improve the accuracy of your model. As I told you, one way, another way could be use feature selection. Feature selection could be done, for instance, by using well, there are some classifier which has their own built-in methods for feature selection. This is the case, for instance, of classification trees. So in that case, but you should of course check the MATLAB documentation, you can run your classification, you can train your classifier by asking him to use just the features that during the training procedure are considered the most important ones. And yeah, for instance, from a classification tree, you can use the function predictor importance, and from the model that you build during classification, it will give you a result on the importance of each predictor. So as you can see, there are some predictors which appear with 0 feature importance, which means that they are probably not used. Actually, you can visualize the classification tree. Wait for a while, that I don't remember how we can do this. I can do this now online for you. It's so easy. You can just use the function view and check for the MATLAB in the MATLAB documentation. So you can actually use view and call the model of the tree to visualize the tree here. So I just run it until here, just to visualize the tree with you for the first time. Okay, so here they display us not the tree, but the decision rules, the if-then rules. And as I told you, this is very nice because it is not easy to find a classifier that is so easy to interpret during the inference process. So most of them are maybe easy to understand from the theoretical perspective, like SVM. It is easy to understand that is trying to find an hyperplane that aims to be positioned in such a way that the classes are far to each other, but this is not easy to interpret then when you go into the inference process and you ask during the classification to see what is happening inside, because there are just combination, multiplication, and algebraic operations during the inference process that you are not maybe able to interpret, to understand. Another common example is the one of neural networks, which are very powerful, but again, it's very difficult to understand why do you reach that exactly kind of combination of weights during the training that leads you to that result. So before moving, I would like to find a way to visualize the graph. So okay, this is one way to visualize the rules, but there is also this in this way we can also visualize the graph. I would like also to visualize the graph personally, so I will add this here and run again. And this is the chart. If you remember, this is exactly the chart that I showed you in the slides, where x3 and x4 are the unique feature that are used by the classifier. So when you run this kind of built-in functions, typically there are already built-in algorithms that helps you to build one of the best classifier in an automatic manner. Here for sure this classifier is built already by pruning the branches that were not useful. And in fact, I think if you ask for the pruning, there may be written somewhere that by default decision trees are trained using a kind of pruning procedure to build a good model without taking care of noisy branches and noisy patterns in your tree. If we keep evaluating this, I would like also to show you that another way to do feature selection is by using the wrapper method sequential FS. Not the wrapper method, but the wrapper method sequential FS, which is a method from which you can do feature selection by specifying an error function, which is defined here, and from this error function, in which inside there is your classifier, which is trained. Okay, here is running the script, so you find new things. And your error function that you pass to the sequential FS function should have a structure like this. You should be able to pass your training set, your test set, the predictors of your training set, the labels of your training set, the predictors of your test set, and the labels of your test set. And then inside you should fit your model and compute the accuracy of your model, which here is computed by first using the function predict and then by using the function non-zero to the logical array that is generated by comparing the predictions and the labels of the test set. In this way, sequential FS is able to give you a binary, a logical array in which you can find which of the features for that specific classifier are really useful. In this case, just the last one, so even one less than in the case of the decision tree. And you can keep going in your process by just keeping the features that are found to be the most reasonable ones. Here I wanted to show you how you can train SVM for a multi-class problem. In particular, if you want to train SVM in a multi-class problem, you just not have to use fit C SVM, but you have to use the fit C ECOC function, which is used by passing a template classifier. So by specifying the kind of learner that you want, which here is template, and template is my template SVM, in which I tell to fit COC which kind of classifier exactly I want to train, which kind of SVM I want to train. By passing the dataset to fit COC and specifying an SVM template, we are able to do the classification of 3 classes problem, in this case with SVM. It is also possible to use fitCOC, asking for the optimization of the hyperparameters, and this is done by asking the optimize hyperparameters property and calling auto, just to let the MATLAB function to do it on its own without your intervention. And if you do this, you will also be able to see what is the behavior of this estimation of the best hyperparameters. Typically, this MATLAB function, with this property enabled, will give you details on the hyperparameters iteration procedures, showing you the optimization problem, how is going the optimization problem for the selection of the hyperparameters, and other few details that you can see here displayed. And again, here I evaluated the confusion matrix of my SVM classifier with just using one feature. And that's it. Actually, I think that this is the result without optimization of the parameters and the other with the optimization of the parameters, but as you can see, they are pretty equal. MDL, CMDL, predicted, let's see, predicted. Yeah, they may be equal. Okay, this was everything by my side for the classification part. I will move back to the presentation. and we should discuss now regression. I know it's a bit late. We are supposed to finish like in 20 minutes, but I don't want to go too much fast because also the regression part is very nice and there's a lot of stuff in this presentation. So please, if you want to know more on this, so if you want a seminar that is less technical but is more a workshop to play on a specific topic, let us know that we can organize another seminar on the topic that you prefer. When we talk about regression, if we move back to our big picture, we are here. And again, also for regression models, there's an application available, which is the regression learner. You can access the regression learner as well as for the classification learner by the apps menu. And then if you have the machine learning and deep learning toolbox, you can locate the regression learner as one of the applications available to you. And okay, so the easiest way to do regression is to do linear regression. And whoops. So again, this is just maybe is redundant by my side, but is for you if you want to see these slides in a second moment. Assume that we have n observations, and each of these observations is a m tuple. So we have m dimensions, m features, m predictors, also called, and these tuples are called x, and they are vectors, of course, because they have m dimensions. And when we have a regression problem, actually we have a response variable y, which is a continuous variable, and the problem of regression is one way to solve a regression problem is essentially to face it as an optimization problem. Typically, what we do is to set an optimization problem, which is like a least square problem or a non-linear least square problem, depending if we are doing a linear regression or non-linear regression, and in which if we have a model that we want to discover, which is f of x and theta, where theta is a vector of parameters, we want to minimize the mean square error of between the labels, the response variable, and the model that we want to fit. So essentially what we are trying to do with this mean squared error cost function, how it is called, is to minimize the difference between the model that we want to fit and the response value that we have. And I remember you that we have this response value because we are in a supervised learning approach. So in the linear case is very easy because this function f is just a linear combination of the predictors contained in the matrix X and the vector of parameters theta. Typically, one thing that you have to do is to have in mind a model to do regression. So you should have not have a model, but at least have in mind a possible model that can fit your data. So in case of linear regression, you are assuming essentially that the predictors of your data set can be used just as a linear combination of them to represent the response variable y. and this is represented by the formula that I wrote to you at the top of the slide. Again, similar as the SVM classification, linear least square problems are convex optimization problems. Before I didn't tell you what convex optimization means, now I do. Actually, this means that all the solutions of the optimization problems, which in general are local minima, corresponds also to the best solution for the optimization problem itself, which means that all the local minima of your function are also the global minima of your function. And this is really nice, as you can understand, because you have the guarantee, you have the guarantee that you'll be able to find the best solution once you set the problem in this way. There are two ways to perform regression, linear regression actually. One way is to solve the optimization problem by iterative minimization. And actually, for this very easy case of linear regression, there is also a closed form solution represented by the normal equation that you see here on the slide. So essentially, you can compute the outcome of your the solution of your regressor, the model of your regressor, even just as a fitting problem by using the normal equation in case of linear regression. And this there is a reason. There are reasons to choose one with respect to the other one, and typically this reason is represented by the size of your data set. So when the size of your data set is very large, computing the inverse of the matrix X transpose times X, which is the matrix of your predictors, becomes a big effort, and it could be faster and easier to just do iterative minimization. There are cases in which iterative minimization is the only way you can proceed. For instance, in nonlinear regression, where you don't have a convex optimization problem anymore, and in that case, a minimization, an iterative minimization is the only way you can use to proceed, because there are no analytical solutions for that specific cases. How to fit a regressor, a linear regressor? You can use the function fitlm, and fitlm takes as input essentially your dataset, and you can also specify a kind of model that you want. So you have to, as I told you before, you have to know in advance a possible model that could be good for your data. This is not always easy to have. And this model should be specified through a string called here model spec, and the model specification, I didn't show this to you now, but the model specification is done using a particular sequence of shared characters which represent your equation, but not exactly your equation, but the terms that could be present in your equation. So, but I will explain this better to you later. You can also fit a linear model without giving a model specification, so just using the automatic not the automatic, but using a particular organizing your X matrix, your matrix of predictors, in a certain manner, so that each column of your predictor is the one that you mean is the predictor that you mean to be useful for your model. Also for this I will explain you better later. So essentially, a regression model is a relationship that can be expressed approximately like this, as a function f in general of the predictors, weighted by a certain coefficients c, which are summed together, so there is a linear combination, and the outcome is your response y. You can specify your input dataset exactly as for the case of classification, in a tabular way, or in a or using array, as I have shown to you here. And you can also specify predefined models for the classification, for the regression, using the Wilkinson-Rogers notation, which is the kind of notation that I told you before, in which we don't express our model with a bad formula like this in a string, but we just use a notation to encode the kind of model that we meant. So for instance, okay, there are some predefined models. You can specify as kind of model linear, and so the formulation, of course, is just a linear combination of the descriptor plus an intercept, a bias. You can also specify the possibility to have interactions. That means you have a linear combination of the predictors plus also the combination of the predictors pairwise, but without having quadratic terms. So predictors can also be multiplied by other predictors, but not by themselves. And you can also specify a quadratic model, which is equal to the previous ones, or as the interactions ones, but you have also the quadratic terms. So there are also terms like x1 square, x2 squares, and so on. You can specify models using the Wilkinson-Rogers notation. I don't want to spend time here. This is just a way to do this. You can see that different operators can be used to address a specific encoding in the notation to obtain a particular formula. For example, the plus operator is used to keep all the terms from x1 and x2, the predictors x1, x2, and also a bias. And there are others. You can also use, for instance, the minus operator to remove some predictors, and so on. Here is the way you have to organize your data if you want to fit regressors. So you can, exactly as in the case of classification, organize data as a table matrix. A table matrix in which you have the predictors along the column, the first, for instance, k columns, and your response variable on the last column. But you can also use array. Okay, as you can see, if you use the table syntax, you should give a model specification. So you should provide the encoding of a model that you want to build. Otherwise, you can use an array syntax which encodes both the things together, because instead of using just the matrix of the predictors, you should use a matrix in which the columns contains all the predictors used in the model. So they are not just the feature, but they are also the combination of features that you want to be present inside the model. So for instance, with a model specification like this, in which you want x1, x2, x1 times x2 and x2 squared, you should organize the X matrix, in this case, if you want to use the array syntax, by providing x1, x2, a column with x1 multiplied by x2, and a column with the element of x2 squared. Okay, I will also mention you that since linear regression is a very easy problem, there is also the possibility to do this without really using fit LM. Okay, fit LM could be convenient in some cases, also because it returns to you some statistical measures that allows you to understand how good was your fitting, your regressor. But for this very simple problem, you can compute the parameters of your model, the theta vector, by this simple, using the normal equation that we have seen before. So by specifying, by computing the inverse of the x transpose times x, multiplying the result by x transpose, and then by the vector of the response variables. Here I just told you that I use P. Typically people use P inverse instead of just inverse, which is the computation of the pseudo inverse instead of the inverse of the matrix, to avoid the possibility that x transpose times x is not invertible. So in this way, you'll be sure that in every case, you'll be able to fit your model, to retrieve your data vector. Okay, this, if you are curious, other stuff for which x transpose x could be not invertible. Another way to fit a regressor is to use the stepwise linear regression, which is a kind of regression technique in which you iteratively add and subtract terms from a starting model. So you start from a model which you assume to be, say, correct, a random model, and then you start by adding and subtracting terms to see and see at each iteration if what you add and what you subtract contribute better in the overall model. And this is based on a criterion, of course. So the function iteratively adds and subtracts terms, then builds the new model. It evaluates the performance of this model based on a criterion, which could be SSE, sum of squared errors, could be the archaic criterion, could be the bias information criterion, could be based on the coefficient of determination. There are many actually, and by specifying the different criterion, you can select different way for the algorithm to select new features or predictors to add or to subtract. Stepwise regression can be done using the stepwise LM function, which takes as input similar parameters as the as the fit LM function. And yeah, also for this one you can specify, if you are using data in a tabular structure, model specification to start with. So using again the Wilkinson-Rogers notation. And then the algorithm will evolve on its own to find what it thinks is the best suitable model. You can also specify an upper and lower complexity of the model by using the properties lower and upper. And also in this case, you can specify the argument of this property by using a built-in model, which could be, for instance, linear, quadratic, or intersections, as we have seen before. Or you can also, in this case, use models which are which you decide to build in a custom way with the Wilkinson-Rogers notation. So as I told you before, in linear regression, the coefficients are chosen by minimizing the mean square error, which means we want to minimize the square difference between the observed data and the predicted ones. The observed data are essentially the labels, and the predicted ones are the predictions that we do with our regression model, where we feed our predictors, and based on a model that we have estimated, we obtain a prediction. In general, you can also use some other regression techniques, such as ridge and lasso regression, in which you add a penalty term in the optimization problem, which means essentially that you are adding a penalty in the computation of the mean square error. And the effect of using a penalty term in the optimization problem typically leads to tuning the coefficients of the model, shrinking them to obtain smaller parameters. This is exactly what I was telling you. So ridge and lasso regression respectively are on the left and on the right side. The same minimization problem as before of the linear regression is this time modified by adding a penalty term, which in one case is a lambda parameter, which is a positive value typically, multiplied by the norm of your parameters, of your parameter vector, which is the sum of the squares of the parameters. Or you can also do this with a lasso approach, a lasso regression, in which the penalty is not the conventional norm that we use for the parameter vector theta, but is the also called the norm 1 or Manhattan norm. I don't know, there are many names for this kind of norm, in which we add as a penalty the sum of the parameters of our model, so the entries of the parameter vector theta, by taking the absolute value. So of course there is a different behavior in selecting one way or another. Ridge regression typically shrinks coefficients continuously and keeps all the predictors. Instead, lasso regression allows coefficients to be set to 0. So it tends to shrink in the same that it behaves like a feature selection. There's also the possibility to have a linear combination of the two terms. In this case, the regularization that we obtain is called elastic net, and we have a linear combination tuned by a parameter A between ridge and lasso regression, that is between weighting with the L2 norm our parameter vector, or weighting with the L1 norm our parameter vector. Yeah, I mean that I know that this could be a lot of calculations, difficult to follow doing a video, but essentially the result of this thing is this. So when you do ridge regression, you typically obtain a model that is tuned by having coefficients that are shrinked. This is useful to avoid a high number of parameters typically, because if you see that some of them are shrinked a lot, you can delete them and use the model without the parameters that are close to zero. Here in this picture you see in reality elasticnet. So the difference by using elasticnet with different values of the alpha parameter, which is the one responsible for the weighting between ridge and lasso regression. When alpha is 0, we have lasso regression, because, when alpha is 1, we have lasso regression. We have no weights on the part of the L2 norm. Instead, when alpha is 0 or towards 0, we have ridge regression. So we have no weighting on the L1 norm, and typically you see that going from ridge to lasso regression, the problems becomes the coefficient shrinks in such a way that at a certain point the models becomes too much easy in a certain sense. So you risk to underfit, because the shrinking is such that it is so heavy that the resulting model is too simple. How to fit a ridge regression model or a lasso regression model with the function ridge and lasso. With the function ridge, you have to specify in the inverted way this time the vector corresponding to your labels, to your response variable, the matrix of your predictors, and then you have to specify a lambda value, or also multiple lambda values, which is the parameter of that tunes the regularization. And you can also specify if you want the predictors to be scaled or not. Actually, by default they are scaled. The result will be what I called before the vector theta, here called b, which is the vectors containing the parameters that should be multiplied by your predictors to obtain your regression prediction. Here there are some other details. The X matrix actually should be built exactly in such a way you built the X matrix before. So since we are using an array convention to pass the parameters, we should pass X organized with all the columns representative of the terms that we want to place inside the model. So if we want a model with 3 columns, if we want a model with x1, x2 and x1 times x2, we should specify X with 3 columns. In one there are the vectors of x1, the vectors of x2, and in the last one there is the vectors of x1 times x2. So again, there are other things. this is more useful to know because it's how to predict based on your ridge regression model. Since the ridge regression gives you a vector parameter, a vector of parameters b, in which the first entry is an intercept. To predict your response variable, you just have to do the product between the new X matrix this time, which is the matrix of predictors, but with new data, of course, if you want to do a prediction, multiplied by the part of your b vector from 2 until the end, so all the terms without the intercept or the bias, and then to sum the bias. As I told you before, you can specify many values of lambda. By default, the algorithm just so if you don't specify lambda, I think by default lambda is internally found by the algorithm, and it will just give you as the outcome also and it will give you the result for that lambda. But if you want, you can specify many values of lambda to see how the ridge regression algorithm works for a different value of the tuning parameter for your dataset. And the outcomes will be, of course, not a b vector anymore, but a b matrix of parameters in which each column contains the coefficients for a particular value of lambda. Again, this is the way if you want to predict for many values of lambda. You will have many values of the response, each one obtained for the different values of lambda. And this is how to do lasso regression instead using MATLAB. You can use the function lasso, in which this time the lambda parameter should be specified by calling the function, calling the property lambda. And also the information of the regressor are not just stored in in B, but they are also stored in the variable fit information, fit info. So it's not completely difficult, but there's a bit of difference. Actually, the function lasso allows you to train also an elastic net regressor. You can specify the alpha parameter with a value between 0 and 1. And other things that you have to know when using this function is that the lambda value that you give in this in the lasso regression function are not treated in the same way as the lambda values that are used in the ridge regression function. To use the same values, you should scale the lambda values in the lasso case by the number of observations. So this is a difference that is inside the two algorithms to take in mind. And again, as in ridge regression, you can use this formula, which is similar but not exactly equal as the one of ridge regression to predict the result of your model. Actually here, B this time is just the bias, is just the intercept, and fit information contains all the other parameters of your model. Oh wait, is exactly the opposite. The intercept is contained in fit information. Instead, B contains all the vectors of parameters except that the intercept. So in fact, here in the reconstruction formula, you see that to reconstruct your data, you have to multiply your matrix of predictors, properly organized again, of the new data that you want to predict, multiplied by b, and then this should be added to the intercept that could be found as a entry in the fit info variable. So the presentation is concluded. This is the whole picture of what we have seen in these two seminars. It's a lot of stuff for just 5 hours. We started by talking about what machine learning is, which kinds of problems can we address. Then we started talking about two possible paradigms, two different paradigms, which are the supervised learning approach and the unsupervised learning approach. When talking about unsupervised learning, last time we talked about cluster analysis or clustering and dimensionality reduction, and we have shown the algorithms that you see in the last column of this slide. We have shown partitioning methods like k-means, we have shown hierarchical methods, we have seen Gaussian mixture models for soft clustering, and regarding dimensionality reduction, we have seen PCA, multidimensional scaling, and in the example that I gave it to you, we have also seen t-SNE, t-stochastic neighborhood with embeddings. Today we saw classification and regression under the supervised learning approach. Also here we have seen a lot of stuff. We have seen KNN, support vector machines, decision trees. I also give you an idea of how ensemble methods works and how to train them, and and possible ways to do regression, linear regression with ridge and lasso regularization. This is the whole picture presented with a MATLAB picture. You can find all the things that I presented to you here in the documentation at the link that I am going to provide you in this slide. And these are this picture actually present you other algorithms that are available for supervised and unsupervised learning, but of course for a matter of time and a matter of problems in presenting all this stuff in a unique presentation, I decided to skip some arguments. And these are the references for this presentation. Actually, these are two very nice books. One used mainly for classification and regression, which is the one of Bishop, Pattern Recognition and Machine Learning, and another book which I used also a lot for the first part, for the part on unsupervised learning, which is the book of Jan Pei and Camber, which is the book Data Mining. I think it's another very useful book for these topics. So we reach the end. We reach the end of the presentation. I think there is not enough time to show you in detail this script, even though it is very easy. Here is you can check it on your own. It's just a regression problem to fit a polynomial from -2 and 2. I generated synthetic data by using the function polyval, which is a function that allows me to obtain the values of the polynomial from -2 to 2 based on the coefficient that I decide of the polynomial.
and then I essentially I perturbed my data a bit with noise, and I asked my regression algorithms to find the real model. There are many ways to do this. I also did this with the easy line of code that I provided you during the presentation, using the normal equation, properly arranging the matrix X. I also did it using FitLM, which I don't see here. I also did it using FitLM. Here I'm just showing you the parts of the fitting where there is the fitting is less accurate, of course, because we are also learning something in presence of noise. And also at the end of the script you'll find the effect of the regularization parameters for the ridge regression and lasso regression. So these are possible approaches to solve this easy problem with synthetic data. I hope you'll enjoy this presentation. I mean, it's not easy to follow all this stuff. I know. In fact, this video could be useful for you to watch it. It would be probably useful for you if you watch it slower than how I present all the topics. If you're interested in doing more practical hands-on on these things, just let me know. You will have all the material available as usual by the link that you find below in the video and also in the Facebook group. Thank you.